Hello. So this is the last meeting of our theoretical computer science seminar this calendar year. Since this is computer science seminar, we sometimes have guests which are computer scientists, and this is the case for Karol, who works at Max Planck Institute in Saarbrücken. And Karol will tell us about fine-grained complexity of integer programming with few constraints.
Thank you very much. It's very nice to be here in Krakow. Thank you for the invitation. So this is based on two papers, and I will tell you first about unbounded ILPs, and then I will tell you about bounded ILPs. So what is an ILP? So it is just on the input of ILP, you are given the constraint matrix. This is just matrix with m rows and n columns. And I will say that delta is the maximum absolute value of this matrix. That's the usual notation in this field. B will be a m-dimensional vector, and it is usually referred to as right-hand side. And C is usually the objective function. And the task in the integer linear programming is to decide if this set has at least one solution. This is feasibility of ILP, or more generally, you want to find the minimum solution, so minimum vector that is non-negative on each coordinate that satisfies this equality, Ax equals b, and that minimizes the objective value. It's important that this objective value is a linear constraint, and this is also a linear constraint. So everyone understands the definition? I will refer to as unbounded ILP because values of x may be arbitrarily high. So state of the art of this for this problem is the algorithm that runs in delta to the order O tilde of m running time. O tilde is a notation that hides polylogarithmic factors. In fact, this is delta to the m log n times the time that is polynomial in the input size. So maybe you are aware of knapsack problem. This is a special case of this problem when m is equal to 1, and indeed for the knapsack problem you have a standard dynamic programming that gives you poly n times delta time algorithm. This is a standard dynamic programming exercise in undergrad courses. And you can extend it to ILPs of arbitrary number of constraints. You pay with this dependence on m in the exponent. And the running time of this algorithm is also like the same in space. So it uses delta to the order of m time and space. And in this part of the talk, I will tell you about the algorithm that is slightly slower. It is like delta to the m to the log delta. So slightly slower, but the space is polynomial. And this was published in ICCO this year. So before I go into this, let me tell you about other regimes of ILPs. So when you have a few variables, there is the algorithm of Tan and Lenstra that runs into to the n log n times polynomial time in the input size. And actually, it is just a branching algorithm, so you can make it work in a polynomial space also. Recently, Thomas Rothfuss and Victor Rice improved the running time to be 2 to the n log n. And this was a Fox 23 best paper. And that's the state of the art. The big open question in this area is whether you can get single exponential running time 2 to the order of n. That would be ETH tight. In general ILPs, as I told you, you can solve it in delta to the order of m when you have a good bound on delta and m. And the special case is a subset sum. This can be solved extremely efficient if you look at the space. So you can solve it in n times b, where b is the target. and to log n log n plus log b space. So it's even much less than what I would promise you. Like I promise you polynomial in n. And for unbounded knapsack, which is the first case when m is equal to 1, it's actually open to get this. Like I visited Krakow in 2018 first time, and with Adam Polak we spent a good amount of time on this problem. We don't know still the answer. But yeah, recently we made some progress with Lars, and we get b to the log b, time and polynomial space. So first I will tell you the baseline, how to combine the already known techniques and to get delta to the log delta algorithm. It will also be quadratic in m in the exponent, so it's bad, but it's very simple. So there is the following theorem. Like imagine you have the ILP. I mean ILP is bounded in this case that the variables are not exploding into infinity. Like it could be that x is like infinite, and we need to assume it's somehow bounded because you have to return the solution, and it is feasible. So it's like that there is solution. Then there is a very nice solution that has a very small support. So the number of non-zero entries of this solution is bounded by m, which is number of constraints times roughly log delta. So that's theorem by Fritz and Schmalling from 2005. They sometimes refer to it as Kara-Theodori theorem for ILPs. And I will tell you the proof. It's simple, but I will tell you the proof for c equals 0, so just for feasibility. So consider the lexicographically minimum solution. There exists solution, so there is some order, and you can select any order actually, and let this x star be the lexicographically minimum solution. And let's just look at the support of this x star. So this is the non-zero entries. That's the definition of support. Okay, and with some non-trivial math, I claim that it's enough to prove something like that. If you prove something like that, then you will iterate this procedure and get this bound. It's a technical annoying detail, but it will be enough to, in fact, prove this. Okay, any questions? So assume for the sake of contradiction that this x prime is large. So 2 to the x prime is also large, like I just exponentiated both sides. Okay? And then observe that because the entries of A are bounded by delta, this constraint matrix multiplicated by x prime, this is a vector somewhere here. Like maximum entry is at most number of entries of this x prime times delta, which is the maximum entry of the constraint matrix, and also minimum. So it's a vector somewhere here. Okay? And by the pigeonhole principle, there are two different vectors that are subsets of these vectors, such that they have the same right-hand side. Right? Because this vector is somewhere here, and the number of possible subsets is greater than the space of the right-hand side. So by the pigeonhole principle, there must be two that map to the same right-hand side. Okay, that's the clear argument of this. So now I will construct two different solutions. So this is x1. This is the solution when I take my x star, my minimum lexicographically minimum solution, and I remove one of these vectors and add one of these vectors, and the other one will be the opposite one. And the killer argument is that one of them is smaller than x prime, because I remove one vector, so at one vector, so one of them must be smaller. But because they map to the same right-hand side, and this doesn't change the value. So it's a contradiction with x prime, x star being the lexicographically minimum solution. Okay, any questions about this theorem? Good. So let's see how to use it. So I claim that as a corollary, you immediately get this rank time. So first, what you are going to do is you do the most naive thing. You iterate over n is the number of variables to your bound on the support, and guess the support. And then you just run a Cannon-Lenstra algorithm on this support. So you will have much fewer variables. So the running time would be n to the gamma. Gamma is this bound from the support bound, and then you run Cannon-Lenstra. Cannon-Lenstra runs in number of variables to the number of variables, so that's the running time. And the number of distinct columns in your ILPs is bounded by 2 delta plus 1 to the m. If there are two columns that are the same, then we can merge it because this is unbounded ILP. So you can assume that gamma to the gamma is much smaller than n to the gamma, and the running time is this. So you get gamma has m in the exponent, and another gamma that has m. So that's gamma to the m squared times log delta. Sorry, delta to the m squared times log delta. Okay, pretty simple algorithm. Any questions about that? Okay. Yeah, so I promised log delta in the exponent, and I promised single exponential in m. So yeah, let's see how to get log delta. And the idea is to do something more clever than just running Cannon-Lenstra. So I will prove the following statement, that if that you can find the lexicographically minimum solution in this rank time and polynomial space. So this is like, this is the L1 norm of your lexicographically minimum solution, and this is your support of this lexicographically minimum solution, and it will be just one factor m in the exponent. Okay. So if so let's see how to use it to get altered for ILP before I show you the proof. So another fact that you can use from ILP literature is the following, that you can bound the L1 norm of the lexicographically minimum solution by this. I will not prove it because we'll improve it later, but you can trust me on that. And log delta was something like that, like log gamma was something like that. Gamma was m times log delta, so you take the logarithm of it, it's this. So you will have this running time for your ILP. So I just plugged in this delta to the O tilde of m, and this to the power m log gamma. This is just single. This is improvement in terms of logs in delta. Okay, any questions? So I will prove, what remains is to prove this branching bound. So that's what we want to prove now, and that's basically the only trick in the paper. So you have some solution to your ILP that has this Ax equals b. It has some support. It looks like this. And I will split it into like first half of the bits of the support and the second half of the bits of the support. Like it will be still like order, so something like delta. And I will branch into left and right side. And the left side will have the property that there will exist a solution that has only this left bits of your solution, and the right hand side will have the right bits of the solution. So I will guess, so naively to guess that, like the first idea would be to somehow guess XL. I'm not going to do that. I'm going to guess B, which is the right-hand side, which is much cheaper. So I'm going to guess this left side of the right-hand side and the right side of the right-hand side. This is this B subscript L. And I will solve AX equals BL. And then I will branch and solve AX equals B minus BL. Okay? And then I will continue and do this in a branching way. So the nice thing about it is that each time I do this, the support halves. So the number of the depth of this recursion will be log delta, because it was log delta bits. Let me tell you it again. So actually what I will prove is something like that. I just changed the bound on the X1, the L1 norm by sigma. So I will tell you the same algorithm, but with a pseudocode if you didn't get it. So in the base case, S is the bound on my support. In the base case, when support is constant, I can enumerate it, like it's just n to the S, that's polynomial time. I can find solution in polynomial time. And then I will iterate over every possible left side of the right-hand side. This is this BL. I'm branching. This is just this many possibilities, because L1 norm of the solution vector is bounded by sigma, and the constraint matrix has entries bounded by delta. So this is how many possible right-hand side there are. This is all the right-hand side that there could be. And I'm just going to solve recursively my LP for this guessed BL and for the half of the support that I have guessed. And I'm going to solve the ILP for this right-hand side, this B minus BL. I don't need to guess this. I know that if there is solution B minus BL. And then if XL plus XR is somehow better than that, better means if both of these calls return in the success, and maybe XL plus XR is, let's say, graphically smaller than that, then I update that. And then I return that. That's the whole algorithm. Any questions? So for the analysis, as I already told you, the depth is just log gamma. This is the bound of the support. And space is also polynomial because that's the number of the depth of my recursion. And the degree of my branching procedure is the size of this green expression here. You can still see green here. And this is sigma times delta to the power order of n. So if you now analyze the size of the branching tree, this is the degree of the branching tree to the power of depth of the to the height of the branching tree. This is this, and this is what I promised. Okay. Any questions? We'll do simple things, I see. Just ILPs. So now I will tell you how to improve this m-square factor. And yeah, as I told you, that was just the only idea that we had. Now we just cleverly combined previous ideas. So that's what you want to have. You have to solve this ILP. And the statement that I'm going to prove now is that is the following statement. I'm just going to have a good candidate sets of the supports. So I will have my constraint matrix, and C will be a set of possible supports. And it's a really surprising theorem. It does not see anything about B or C. It works just by saying A. So each of these vectors in this candidate support set will have a small L1 norm bounded by gamma. And for every B and for every C, that there will be some optimum solution that has exactly the support. Like the input is completely oblivious to B and C, but somehow it works. And the theorem that I'm going to prove is that this set is bounded, is small, but actually it can be also efficiently enumerated. So it can be enumerated in delta to the m times log gamma time. Log gamma will be roughly log m plus log delta. So this will give us the rank time. Yeah, and the space is also like polynomial to enumerate this set. Okay, any questions about the definition? Yeah, and the algorithm will be just, now I have all these candidate support sets, so I will go over this possible candidate support sets. And I will solve my LP by using Cannon-Clare-Stride number of variables to the number of variables. And the running time is just the number of possible candidate support set, that's this term, and the number of, and the running time of the ILP is gamma to the order of gamma, and this is, actually running time of ILP is now much smaller than even enumerating this candidate support set, and that's the claimed running time. Okay, any questions? Okay, so let me prove the step.
Wait a little bit some time.
Yeah, Lenstra-Cannon works in polynomial space. So yeah, that's the objects that we want to enumerate, and I need an algorithm that enumerates it in this time. And as I said before, I don't have any new ideas. That's the idea from the previous part. So I will just iterate over every possible right-hand side that has a small infinity norm. And I will use this branching procedure for every of this possible right-hand side. And yeah, this branching procedure actually didn't use anything about C. So that's where C is hidden. And the nice thing about B is that I will do this for every B, and because it's small, it will work. And okay, and then I will do this. And then I solve this and add this solution to my candidate support set if it exists. So recall that the branching procedure was able to find the solution in this running time, and this should give you the running time now. So this is like delta to the x to the L1 norm of x star. This is bounded by the gamma. So this is gamma to the m of gamma times delta to the power of m log gamma, which is what we want. So correctness is a bit tricky, but it's actually a couple of paragraphs, but they are very dense. The idea is that if you have lexicographically minimum solution, let's say it's at star, then there exists this right-hand side that basically for this right-hand side the solution is just the support of this at star. That's the intuition. And okay, for this particular x prime, that is just support of your lexicographically minimum solution, the right-hand side will have a bounded L infinity norm because it has bounded L1 norm, and the maximum entry of A is also bounded by delta. So that's pretty much the proof. And the running time is, as I said, this is the number of possible right-hand side in this branching in this for loop, and for each of this for loop, I will run this branching procedure that has this rank. And yeah, this doesn't matter because that's much smaller. And then I plug in what is gamma. If you forget about it, then this is just m log m times delta, and that gives you the running time. So to summarize, every step is polynomial space, and what we wanted to solve is this. So first, what we have is one trick in IAP that is just Kara-Theodori theorem by Eisenbrand-Schmonin, and then you enumerate possible supports in the number of in the size of C time, and then for each of the support you solve ILP. Yeah, you use this branching procedure to bound this running time to bound the size of this possible support set by delta to the m log gamma. And yeah, then the observation is this, and that gives you the running time. Any questions about this part? Okay, so let me move to binary ILPs.
Okay, Karol, so maybe so you prove the dependency on delta. What is like the barrier here? What is like
yes, I will talk about it in the summary.
Okay. Are there any lower bounds?
Yes, so this is ETH tight. And so you cannot have delta to the little o of m.
Okay.
And yeah, so, but yeah, it works in polynomial space, in exponential space, in the number, in the input size.
Mm-hmm.
And
yeah. You mean that the lower bound is in polynomial space?
No, it's ETH lower bound. That doesn't care about space. Like what we want to do here is polynomial space, but we have a bit higher running time. So yeah, it's very possible that you can still improve this log in the exponent. Yeah.
So which hypothesis there is some
ETH, exponential time hypothesis. Yes, I don't even know how to do this for m equals 1, and yeah, how to avoid this log delta.
Okay, thanks.
I still don't know that. But yeah, the dependence on m is almost optimal, like just one log factor away. So now let me tell you about another hypothesis that I just came up. But before that, let me tell you about the problem. So now bounded ILP, that's what I will call, is that you will have some bounds on your variables. This will be Li and Ui. So each variable will have some lower bound and upper bound.
Wait, is it a lower bound and an upper bound, or just two possible bounds?
Sorry, there should be dots here. Yes, it's a mistake. There should be dots. I forgot to put C dots. Sorry. The way I think about it is actually R is equal to 0 and U is equal to 0. That's why I forgot to put the dots. That's actually important special case. Then it's called binary ILP. If you have this, then you can think about, for example, subset sum or standard knapsack. When you take your item, you either take it or you don't take it. So this is easier problem or harder problem? What do you think?
Easier or harder than what?
Than the previous problem. So when I have this upper bounds and lower bounds, is it easier? Or when L is equal to 0 and U is equal to 1, is it easier or harder?
Will be harder.
It's harder, yes. And the best running time that is currently known is delta to the m square. Yes, it's really surprising that that's the state of the art, but yeah.
So is it because these kind of arguments, like with that pigeonhole,
Exactly.
don't work?
Karate-Odori theorem stops working in this case, and yeah, we don't know how to get anything better than delta to the m squared currently. Like Fritz spent significant amount of time trying to match his algorithm for unbounded and bounded ILP. Yeah, we still don't know. Yes, and the best lower bound is, as I said before, the same as for unbounded. So it's possible that there could be delta to the order of m algorithm. Okay, and yeah, we tried to prove some lower bound for that, and we failed. But what we have managed to prove is a bunch of problems that are equivalent to this problem. That's what I'm mostly doing in my life, finding equivalent problems. So binary ILP and this bounded ILPs are equivalent, and yes, and actually binary ILP is equivalent to other problems. One of them is closest string. So in the closest string problem, you are given m strings, each of length n, and some alphabet, and the task is to find the string that is closest to each of them. So it basically means the one that minimizes the Hamming distance. So in this example, I hope I didn't make a mistake.
So A and B are strings at the last line, not letters, right?
Yes, these are the strings, these are the letters.
Okay.
Yeah. Sorry.
This is like minimum radius small.
Yes, but in Hamming distance.
Oh.
Yeah. Yeah, so this is called closest string. It was defined like this. And yeah, an example would be like you have this three strings, and the optimum solution is this one. So you can have some errors here. And you can solve it in 2 to the m squared time. M is the number of strings. When size of the alphabet is 2, there are also different parameterization that you may know. That there are parameterization by the minimum Hamming distance, but there is also this parameterization. And if you could get faster algorithm, then you would actually solve ILPs faster, and on the other way around.
What is M here?
M is the number of strings. Mm-hmm.
N is the length, yeah?
N is the length, yes. So there are different parameterization that are parameterizing by the length. These are a bit different.
By this general ILP, you mean this binary?
Yes, with some bounds. We also found the following problem that's called discrepancy. So in this problem, you are given some universe and some family. You will see a pattern soon. And the task is to find some coloring of this universe into like negative or positive colors, such that in each of these sets, if you want to minimize the discrepancy between ones and minus ones. So the task is to color elements into two classes so that these classes are spread as evenly as possible. So I have this example. So you have universe 1, 2, and 3, and set S1 being 1 and 2, and set S2 being 2 and 3. Oh yeah, you can see the colors. I color this into blue, this into red, this into blue, and then discrepancy is 0. Each of this subset has even number of ones, even number of red and blues. Okay, understand the problem? So another example, I have this sets 1, 2, 2, 3, and 1, 3. And there is now no way to color this universe into two different colors such that each of them has, and there is no way to color this set into two different colors unless I make mistake, so that each color has, each of this set has different colors, the same number of colors, because each of them has two. Okay, you understand the problem? And yeah, you can also solve it into 2D O tilde f m square. And surprisingly, if you could improve this to be like 2 to the m to the 1.99, you would improve all bounded ILPs and all of these problems that I talked about. Any questions?
So the sizes of these sets are not important?
No.
Mm-hmm.
I mean, probably if you could, if there are like constant, probably then you can solve it faster. But in our reduction, it's high.
Reducing to ILP looks easy.
Hmm?
Reducing to ILP looks easy.
Yes, showing equivalence is hard, I think. Yeah. Yes, you can solve it using ILP easily. What's surprising is equivalence. We also found this problem to be equivalent. So you have, this is called set multi-cover. So you are given some universe and bunch of set families and bound B. And if you know standard set cover, then B is equal to 1. You want each of these elements to be covered by at least one of the sets. Here it's a bit different. You have this bound B, and you require that each of these elements must be covered by at least B sets from your family that you select. Okay. And similarly, you can use ILP to solve this problem in 2 to the m square time. And yeah, improving this would also improve general ILPs. And yeah, we also have some dual problem that was called set multipacking. That's equivalent. So basically, we managed to prove all of that. Like we managed to prove discrepancy, closed string, set multicover, set packing, and set multicover are equivalent on their own because there are duals of each other. And we show that all of these problems are equivalent. We also have some other hypotheses that we call strong ILP, and in that reduction you require that the delta is exponential in m, and this gives us the lower bound for something that we called n-fold. People looked at this special case of ILPs. These are solved in 2 to the n cubed time. Yeah, so which requires us to have delta to be of order 2 to the m. And yeah, so let me state the hypothesis maybe.
So here I don't understand something because you are saying that these problems are equivalent.
Yes.
But before you gave us an algorithm with just single exponential in m for ILP.
Yes, but it was ILP with when the variables are needed to be non-negative. And here I have some upper bound and lower bound on the.
So this ILP here means the one with upper and lower bound.
Yes. So, sorry for the slides. For the figures. But this is like binary ILP. So I'm saying these upper bounds and lower bounds don't really matter. You can use some tricks to reduce to 0, 1.
I was asking about the top one.
Yeah, this is with upper bounds and lower bounds. Yes. So sorry for. It should be like bounded ILP maybe. That's the good name.
So in binary ILP, your matrix is binary?
No. In binary ILP, X might be either 0 or 1 to the end. Sorry.
In the slide, additionally, your matrix is binary.
Where is it? So this variant I call binary ILP.
Okay.
The constraint matrix is not really binary. It does not have to be binary.
But here it has to be.
Here.
No.
Yeah. So it's even more restrictive setting. Like we can even make that delta is just 1. And that's also equivalent to everything. When delta is constant. When delta is non-constant, then I don't know how to prove equivalence. Mainly because the running time is higher. I've currently best algorithm for ILPs in this case. Let me restate the problem. So can you give this algorithm for this bounded ILP? Sorry, I should have write binary ILP here. And yeah, as I already mentioned, it's quite surprising that you can do something better for unbounded ILPs. Like this is delta to the order of O tilde of m. And this is ETH tight, and we don't know how to do this. So what we did is to state this ILP hypothesis that there is no 2 to the m to the 1.99 time algorithm for ILPs with bounded entries and some constant delta. Okay, that's the hypothesis that we stated in the paper. I would be very interested if you could disprove this hypothesis. I don't know how to prove ETH hardness. We also stated the following hypothesis. It's even stronger. It's that you cannot solve this problem even in time delta to the m to the 1.99 for delta being of order 2 to the m. When it's larger, you can do this actually. So yeah, I'll give you this two new hypotheses. Maybe you can prove more equivalences to it or some other hardness based on that. It's nicer because there are these algorithms for n-fold that you prove tight, assuming this hypothesis. And yeah, can you even have even stronger hypothesis? Actually, no. I can solve binary ILP in this time, actually, bounded ILP in this time. So if you don't require to be FPT in delta and m, if you are happy with factor that is n to the m plus 1, then you can do this in this time. This is the bound on the largest and on the upper and lower bounds. So just polynomial. Okay. Let me tell you a nice statement that we use in ILPs a lot. And this is something that we call cover. So I'm not sure how surprising it is. It was quite surprising to me. It is not when I see the proof, but so imagine you have some integer k and some other bound on h, and you have some bigs. You can produce some bigs, some number between 0, 1, and 2, such that this set from 0 to k, is basically equal to this. So this is like xi's are bounded between 0 and this bound ci of k. This is just the number between 0 and 2. And this set will see every other set between 0 and k. You can produce any integer between 0 and k. That's a nice statement. It took me a few days to prove it. Yeah, feel free to think about it. I will show you the proof later.
So wait, I didn't process it. It feels like you're representing
And a number, yeah. Yes.
So why isn't it just trivial if I have 0, 1? If k is h is model of k. So
yeah. If k was a power of 2, then it would be trivial, but k is not necessarily power of 2.
So say if k is then
then you need this extra carries here.
That's why you have the second value.
Yes.
The third value.
Yes.
Oh, okay, I see. Thank you.
So this is extremely useful if you have like large upper bound and lower bound between your numbers. Then you will represent it as logarithmic number of constraints that are just between 0 and 2. That's how you should think about it. That's another trick.
So it's not just a cover, it's like a cover that doesn't stick out.
Yeah, I'm not the best person to name things. Yes, I named it cover, but I don't know how to name this. Yeah. And let me tell you how to use this to solve this ILP. That's not really interesting part. The interesting part is proof of this statement. So you imagine that you have this ILP, you want to solve this. These are the powers of, you can rewrite this as just, you have some variable, this variable has some upper and lower bound. Let's assume lower bound is 0. By just scaling, we can assume this. And now you will use this cover to represent this ILP as logarithmically many variables that have just upper bound 2. And this is how you want to use this cover to represent the number. This will basically enumerate every possible right-hand side. This is where this came from. And with some straightforward DP, you can solve ILP in n to the m time by doing this. It's not that interesting how to write this DP, but you can trust me that you can do this. And yeah, it's not non-trivial to bound this. Let me tell you this proof. I'm very happy about it. I actually rewrote it again, but I hope it's crisp. So you will just write this these two numbers. This is the number B and the number T. I just call them bottom and top bits of the number K. And I will enumerate this set as B. This is just the set of the following set. So I will have numbers xi being between 0 and 1 when this is binary representation of this number, which is 1, because this is just 2 to the h minus 1, so each of these numbers is 1. So yeah, I create this set, and this set is just this. So this answers our question when k is equal to 1, I will just put 0 ones here. And now I have this set st, and this will be the bits of the number t. So yeah, that's the set. And my CI will be just this binary representation of this ith bit of B, and I add binary representation of the ith bit of T. And this number is between 0 and 2 because this is the sum of 2 bits in the worst case. And what you need to observe is that I add these two numbers, and these are all the numbers between 0 and k, because sum of B plus T is k. And if you look at ST, then the maximum gap is smaller than 2 to the h. And this, yeah. And because h is larger than log k, this will hold. Yeah, previously I had much more complicated proof. I even managed to generalize it more. Yeah, so actually we used it in 3 papers. Okay, so it's almost an hour, so let me conclude. So ILP is the following problem. You have some constraint matrix, some right-hand side, you want to find x such that Ax equals b. This is feasibility. You also want to minimize the subjective value. This is optimization. and people are interested mainly in this case, also primarily in the case when delta is bounded, because otherwise only exponential time algorithms are known. In the first part, I showed you this algorithm when upper bound was infinite, and the running time was this, very ugly expression, but the space was polynomial. Yeah, I was told that maybe it could be even made practical because space is polynomial. That's what Fritz said, but yeah, I never implemented it. Sounds like a good exercise. And in the second part, when U was not infinite, then the problem has then the problem has 2 to the m square algorithm, where m is the number of constraints, and improving that would yield a faster algorithms for ILPs when the number of constraints, when delta is constant, when you have bound being equal to 1, when you want to solve closure strings with binary alphabet, when you want to solve discrepancy, the set multi-cover, set multi-packing problems. The open question that I'm really interested in is this case of unbounded knapsack. Can you give this algorithm for unbounded knapsack? Can you get rid of this log delta in the exponent, in other words? I think it's a very nice question. Thank you.